Hi guys, my name is Mr. Lead, and today we're going to be talking about light. Now, light is a form of energy. We've discussed that already, but we're going to discuss today how exactly light works. The first thing you've got to understand about light is that light travels in waves. More specifically, they travel in transverse waves. We discussed that in the last lesson. Now, unlike sound, light doesn't actually need matter to travel through. So remember how sound traveled in waves, and it had to travel through the energy passed through the vibrations of matter, passed through the vibrations of particles. Light doesn't need to matter to travel through. So that means in space, you can't hear anything. Sorry, Star Wars, you can't hear explosions, but you can see things in space. In the vacuum of space, light is supposed to travel at a given speed, and it's the fastest speed known to man. It's this speed. That's pretty fast. But even with that speed, it still takes the light from the sun 8 minutes to travel all the way and get to Earth. That means that the sun and Earth are actually really far apart. Now, to properly understand what exactly light is, you need to understand what electromagnetic radiation is. Now, hold on here. This can sound really confusing, but let's just dive in and try to understand what exactly electromagnetic radiation is, because you've heard of some terms of what electromagnetic radiation is already. You probably just don't even know it. So, electromagnetic radiation is a form of energy. Electromagnetic radiation travels in waves, just like sound, but unlike sound, electromagnetic radiation doesn't consist of matter. It's not made up of atoms. It's not made up of anything you can feel. It's just, but we can actually see the effects of electromagnetic radiation. Now, some easy examples, some prime examples of electromagnetic radiation are gamma rays and X-rays, ultraviolet light, the visible light that we're talking about today, infrared light, microwaves, and radio waves. All of these are different types of electromagnetic radiation, and the thing that makes them different from each other is their wavelengths. So remember, electromagnetic radiation are waves, and just like sound, these waves have different wavelengths. So that's from peak to peak. That's the difference between them. Now, when we talked about sound, we talked about how the higher the pitch, the shorter the wavelength. When you look at electromagnetic radiation, if you see electromagnetic radiation with a really short wavelength, it's going to be a certain type. So gamma rays only exist with a really, really small wavelengths, and then X-rays with a little bit bigger, ultraviolet light with a little bit bigger, and so on and so on. If we were to actually measure it out, radio waves, if you just took and found a radio wave actually has waves that are kilometers long. It's really, really long. Once again, remember, you can't see any of this energy, but you can see the effects of them. Say, for example, you can see the effects of microwaves in a microwave. They're used to heat up things. But the only type of electromagnetic radiation you can see is radiation with frequencies at around this range. That is what visible light is made up of. Now, visible light is made up of different colors. So we got red all the way to indigo and violet, the colors of the rainbow. So every single color of visible light comes at a different wavelength. So if you were to theoretically take a beam of red light, and you can't do this, by the way, but if you were to theoretically squish that red light together a bit, you would change its color and it would become purple light. Likewise, if you took a red light and you pulled it apart, you would pull it apart so much so that it's no longer visible light, so you can't see it anymore, and you could keep stretching that wavelength out until it, say, becomes infrared waves and microwaves and radio waves. Again, that's not something we can actually do, but if you could theoretically do that, that's what would happen. Now, light, like I said, comes in different wavelengths. So you see down here, red has the really long wavelengths. Violet has much shorter ones. But you'll see here there are some colors that are not represented. What about light? What about white? And what about black? What about those colors? Well, maybe you're not actually wondering about those colors because you might be thinking white and black are shades. I learned that in primary school. And yeah, you're right. White and black are shades. White is not a color. White is just a combination of all colors. So when you see white light being shone at you, say for example the sun is always shining white light at us, it's actually shining a combination of all the different colors mixed all together. It was Isaac Newton, a very famous scientist, who discovered that white light is made up of all these different colors because he discovered you can get a glass prism and you can disperse them. You can split apart all these colors to see the different color. To see each of the different colors. Well, this is going to really work on camera. But if you take a white object and you look at it through a glass prism, you'll see that object. Hang on. You'll see that object gets. The white object you can actually see is the light being dispersed there, and you can see a rainbow effect. Yeah, it doesn't really come out as well on camera as if you were just to put it up to your eye. But nevertheless, that is what light is made of. Light is made of electromagnetic radiation, and white light consists of all light put together. What about black light, though? What is black light made of? Well, black is just the absence of light. Black is not made of any light at all. Now, we're going to discuss what happens to light when it interacts with matter, when it interacts with some sort of surface or medium. Now, when it interacts with something, light can do one of three things. Or technically, it can do some other things, such as diffraction, but we're not going to talk about that. Light will do one of these three things. It will either get absorbed, it will be reflected, or it will be refracted. All right, so the first thing, absorbed. Now, bear with me on this idea because this is going to get pretty complicated. An object will absorb whatever color it isn't and will reflect what colors it is. All right, now let's dissect this idea a bit further. Let's say you take some white light, say the white light that is coming from this lamp that you can't see. You take some white light and you shine it at a blue object. Now, because the object is blue, it will absorb all those different colors of that white light, say the red, orange, yellow, green, indigo, and violet. It will absorb all those different colors, but it's going to reflect blue light because it is blue. It's not going to absorb blue. So that is how absorption works. An object will only absorb whatever colors it isn't. So if an object is white, it's going to reflect any light that is thrown at it. But if an object is black, it will absorb all light that is thrown at it. This is why when you wear a black t-shirt, you actually feel hotter than when you wear a white t-shirt, because that black t-shirt is absorbing all that light and converting it into heat energy.
Let's explore this idea further. So right now, the only light found in this room is the light from this torch right here, and it is emitting white light. This white light is being all absorbed by this blue pen, except for the strands of blue light that is within this white light, and that blue light is being reflected off this pen. I'm not sure if my camera will be able to do this justice, but now that I've got blue cellophane over the torch, the white paper is now appearing blue because it's only reflecting blue lights. That's the only light that's existing here. The pen still appears... it's a bit hard to see with the camera, but the pen, trust me here, the pen still appears blue because the pen itself is blue. And so therefore it's able to reflect that blue light back still. But now that I'm shining green light, this paper, which was originally white, now appears green because that's the only light there is to reflect. But the pen, which was originally blue, now appears black. That's because, remember, an object only reflects whatever color it actually is. So if there is no blue light to reflect off this blue pen, then whatever other light that is shone on this pen will just be absorbed and it will look black. You only get to see an object if it is reflecting the light. This pen here, we don't get to actually properly see it because it's not reflecting any light here. It's not able to reflect that green light.
Remember, if you can see any sort of light, if your room isn't pitch black and you can see some sort of light, that means there is light already in the room. There is light bouncing off and reflecting off the room in all sorts of places. If you can see anything, there is light in that room. Right now, light is already being reflected off the walls because the wall is naturally a cream color and cream light is being reflected off it. Right now, light is reflecting off me and into the camera as well. The light reflects, though, is with equal angles of reflection. So light will always bounce off an object the same way. It will have what's known as an angle of incidence and an angle of reflection. It will always bounce off in this really uniform way. Now, this angle of incidence is always going to be equal to the angle of reflection. So say, for example, light comes in and bounces at a very low angle of incidence, it will have a very low angle of reflection. Likewise, if it's got a really high angle of incidence, it will have a really high angle of reflection. Now, you might be wondering maybe, well, what about curved surfaces? How does light reflect there? Well, again, it will still reflect with angles of incidence and angles of reflection, but every single beam of light will have a different angle of incidence and reflection from each other. So the light wave coming here will interact with the tangent on this curve different to the light wave coming here because this is a different tangent. So this light wave comes in, has an angle of incidence and an angle of reflection. This one has an even smaller angle of incidence and reflection. This one doesn't have any angle of incidence and reflection. It's just zero, goes back out. So each one of these bounces off at a different point. And so what you end up getting is, with a concave mirror, you'll see a reflection being turned upside down. This is what happens when you look at a spoon and you look into a spoon. Your reflection is actually upside down because the light that was up here to begin with has ended up down here. And the light that was down here has ended up here. With a convex mirror, it's a bit different. Light is being scattered in different directions, and you're going to see your face. It's not upside down, but it'll be very lopsided instead. By the way, if you want to try and remember the difference between concave and convex, a concave curve will be dug in like a cave, but convex isn't. All right, it's reflection. The final thing to note and to learn here is refraction. Now, what you got to understand before you understand refraction, light is going to travel at different speeds through different mediums. What I mean by that is, if you were in the vacuum of space and there was no matter present and inhibiting light's travel at all, then you're going to see light travel at the speed of light, at almost 300,000 kilometers per hour. But if you look in air, light will just slow down by a tiny, tiny fraction. It's not really enough for us to actually see light physically slow down, but we see an effect of light slowing down. And this effect is known as refraction. So this is more easily seen when you see an object put into some water.
So if we took a straight object, like a pencil, and we put it in water, we would notice the effect of refraction. This pencil, which was once straight, now actually looks slightly bent if you look at it from certain angles. So if you look from down here, you can see this pencil is not as straight as it once was. That is because the light that is traveling from the ceiling, from the light bulb in the ceiling, that is traveling through the air, through the water, reflected off the pencil, back through the water, back through the air, and into this camera lens, is now having to travel at a slower rate because of the water than just the light that is traveling through the air, hitting the pencil, and then back through the air into the camera lens. The water is slowing down the light, and it's this act of slowing down light that actually causes the light to bend. So light gets bent in certain mediums that causes it to travel slower, and that is what refraction is. You'll notice glass actually has the same effect, but probably to a lesser degree. Glass causes light to bend less than what it bends in water. Light travels faster in glass than what it does in water. But what if we had two substances at which light traveled the same speed through? Well, this is not just glass. This is called Pyrex glass. And in here, I have olive oil. And light actually travels through Pyrex glass at the same speed as what it travels through olive oil in. So that means that when I put this Pyrex glass into here, and I fill fill it up, it actually becomes, and I stand it upright, hang on, and I stand it upright, it actually becomes invisible. You can see it just barely on top, but you can barely see it on the side. Right there. Yeah, you can barely see it now because light is now traveling through these two medians at the same speed. Now, what you might not know, I put one test tube just in here, but I actually had some test tubes in here already. Plot twist, there's another one. And another one. They were hiding in there the whole time and you didn't see them. Or you probably didn't see them. I don't know.
We actually make use of the idea of refraction when we're making lenses or glasses. Because light waves, remember, light waves bend through different mediums. If we cut a certain glass in a particular way, we can make it so that the light will bend for a certain period of time, and then will be stay bent at a certain angle. So if we have convex lens, that means we're going to make the light bend into a certain point. This is what happens with a magnifying glass. You can angle that point and focus that point to convert light energy into heat energy and start a fire. If we had light going through a concave lens, concave, dug in, cave. If we had light going through a concave lens, then it will come out spreading out like this, and that's made use by projectors. Now, when we talk about our own glasses. Glasses are used to correct focal points that our eyes aren't going to do well by themselves. So with normal vision, the biological lens in your eyeball is made to focus all that light, so it's a convex lens, is made to focus all that light down to a particular point at the back of your eye called the retina. But if your biological lens isn't quite perfect and it isn't made to focus that light right at the back of the eye, it can either cause you to be what's known as nearsighted or farsighted. If you're nearsighted, that means you're not going to be able to see distance. If you're farsighted, you can't see what's close up. So nearsighted people need a concave lens to correct this. A concave lens will spread the light apart a bit so that it can reach the back. And for far-sighted people, they don't want it to reach the back. They don't want it to reach it's reaching too far back. With far-sighted people, they need a concave lens to direct the light in a bit closer into the lens so that it can reach the back of the retina correctly. All right, so that is the topic of light. There was a lot involved, I admit, but it's a really fascinating topic, and there's a lot more that we could go into, but we'll leave it there. Thanks for watching.